nowadays. It's a great pleasure to be here. I was convinced by Martin Escardo, who's out smoking at the moment. There you are. That this is something worth talking about. So it's an exploration of higher type computation. In essence, I'm going to talk about what happens when you have higher type computation and you add computational effects. What do they give you? Can we do anything nice and interesting? So let me recall Hilbert's Epsilon. We want this. So there is Hilbert's Epsilon. It's something that takes a proposition from on a given set X and returns a witness. And the condition is that it should return a witness such that it holds P holds of the witness if it's possible for it to hold, if there is any X at all such that P of X holds. So this was Hilbert's Epsilon. And we can ask whether we can implement this sort of thing. So if we implemented it on some data type, the easiest way to have epsilon would be just to consider decidable predicates. So this would then have to be something of type x goes to booleans to x. So if x is something like a finite data type which has 17 elements, then this is easy. You just go through all of them in your search. But what is maybe more surprising is that there are infinite data types, namely the Cantor space. For example, if you take x to be the Cantor space, which would be the natural numbers or just the integers into booleans, then you can also produce an epsilon. And so this, let me show you the code for it in Haskell. So here's this data type Cantor. These are just shifting operations. It takes an infinite sequence. So the hash takes an infinite sequence A and prepends the bit X to it. So here's a version of epsilon that you might actually attempt to understand if you haven't seen this before. The epsilon prime. So you just sort of do a strange thing. You say, well, let's see. So either there exists a sequence A such that P holds when I start with false. Okay, so I say, is there a sequence A such that P will hold of the sequence false followed by A? If so, then my output is a sequence false followed by whatever epsilon is going to find for the tail. Otherwise, it has to be true and followed by whatever epsilon is going to find for the tail. So this is a recursive function. It's definable in PCF. And it's a mutual recursion between exists and epsilon, but that's sort of not important. The important bit to observe is it's purely functional, definable in PCF, and it's recursive. Martin Escardo has taken this to new levels of efficiency. Namely, this is going to be fairly inefficient because it just keeps branching off. So it first branches at the first bit of the sequence, then it branches at the second bit of the sequence, then it branches at the third bit of the sequence, and so on. So for example, if the predicate P is just something that is testing the 100th element of the sequence, we're going to get 2 to the 100 steps done before we ever get to the 100th element. Although I should warn you that arguing about the time complexity of these things doesn't seem to be an easy thing, and it doesn't even seem to be easy to explain what it means to argue about the time complexity of these things. So here's a version by Martin, which I'm not going to try to explain in detail. But what it does, it's a clever branching where you don't look at the sequence as just a sequence of bits coming one after the other. It's splitting the sequence into the first bit and then the odd placed bits and the even placed bits. So it's splitting my sequence into two sequences. And the effect of this is a kind of a search, a binary search, which makes the thing much more efficient in many examples. I suppose I can run this. No, so you say, give me a sequence such that, what do I want?
It's Haskell.
Oh, it's Haskell. Yeah, I have to keep switching because later on I'll switch to a camel. So this is getting, yes. Okay, so give me a sequence such that the 10th place is different from the 20th place, like that. Is not there? No. Okay, I'm confused. Yeah, so anyway, the answer is a function. No, the answer is a function, so it doesn't want to show me the function. Yeah? It says I found a function, but I don't know how to show. So I'm going to tabulate it. Okay, so I will say, well, let f be the function you found. And now, what is f of I? I goes, what, in something like 0 to 30. Will this work? So you see it goes true, 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 false, true, because I required that A10 is different from A20, and then something goes on at A20. Okay, so it finds something. So you can try this with larger values. And you write here something, go like this. And then you ask, well, the obvious thing to ask here would be what is G at that place and so on. Okay, but unfortunately I don't have the time to play with this. So I'm not going to play with this. You can play with it and you notice that the epsilon prime is much slower than the epsilon. And that the epsilon is in fact amazingly quick about finding things. So I asked one day, well, these things are purely functional. Can we get anything out of having computational effects? Can we write epsilons which do something else than these things? And so that's what I would like to show you. But before I show you the epsilon, I just want to show you an example where you must use computational effects to achieve something that you want to do. And that's the modulus of continuity. So let me just remind you what that is. So if you have, no, wrong way, this way. So if you have a function f from the bare space to n, and then the modulus of continuity is something that is going to take the function and it's going to take an alpha, and it's going to tell you how many bits, how many terms of alpha do you need to know to compute f of alpha. So this is something you can actually compute if f is continuous. If f is continuous, then it only depends on some initial segment of alpha, and you want to know what amount suffices. So this is supposed to be a k such that whenever you have beta, which agrees with alpha in the first k places, so this just means the initial segment, then f of beta is going to be the same thing as f of alpha. So now this you cannot define in PCF or Haskell. And the reason is that every total functional that you define in PCF or Haskell is extensional, but there is no extensional modulus of continuity. These things are well known. And so this, if you want to implement this, you must use something that's not purely functional. Here's an example. Now this is OCaml. I'm going to use one local reference to discover how far f has looked. My f has, so this is my f. I have suddenly changed all the notation. So here's my functional. Maybe I dare change it like this, okay? Okay, so I have a function f, and I want to discover how many terms of alpha it needs. So I produce a secret local reference that nobody knows about. It's very important that this reference is local. If it's global, then f could play tricks on me by changing it. And then I produce a new function, beta, which acts just like alpha, okay? Except that every time you evaluate it, it remembers the maximal value of wherever it was evaluated up till now and n, okay? So the reference R, after you evaluate f of b, after you evaluate f of b, the reference is going to contain the maximal value at which f has evaluated b. And so you will know the modulus of continuity. Maybe I have to add one here. It's irrelevant. Okay. Yeah, so does this work? Who knows? Maybe it works. So we try something like this. I have a functional which takes a and evaluates a of 10. And I apply it to the sequence of squares. So what am I supposed to get? It's going to evaluate 10 squared and then again squared. So it's going to go up to 100. So presumably this is going to be 100. So you see that source code can work even after you have modified it. Now, this is impossible to do in a purely functional language. Because my main example, the epsilon that I want to show you, is going to be written in F, which is a new experimental programming language using algebraic effects. Let me show you how this functional, what this functional looks like if I convert it to F. F has OCaml-like syntax, but it has certain things that OCaml doesn't. So the first thing to notice is in F, so to speak, is a pure. It's a pure language in which you can then define your own algebraic effects. And so while you're using an effect, it looks like it's an effectful computation, but on the outside, it looks then it looks pure. So here's how I will do it. I will first define the computational effect of references. And when you define an effect type, you have to specify what the operations are. So for a reference, we have two operations, get and put. Get takes a unit and it gives you the current content. And put takes the value and stores it. When I write this part here, that is not actually telling you how. This one is just declaring functions. This is just a signature. It's not telling you yet how get and put are supposed to behave. So here's my mu, which is exactly the same as before. So I have an F, I have an A, alpha. I want to discover where it is. I create a new reference. Then I create my B, which acts just like A, except that it's secretly recording the maximal value at which it has been so far evaluated. And then I do the same thing as before. I evaluate F at B. F is going to think it's got A because it can't tell the difference between A and B.
Just ignore.
Ignore it just means throw away the result because the result is going to be an integer and you have to do something with it. So you just say ignore. Ignore is a function which takes an argument and it returns unit. Okay. And then you look at what's stored in there. And this is how you implement local store in F. So you have a handling construct here, which, see this new ref, this just creates an instance. It's like a new name generation. So here you actually explain what happens. So if get happens on R with some argument unit, then, and now this K is the continuation. It's the rest of what happens after the get. K is the thing that you're supposed to tell what the value is. You will recognize the usual Haskell-style monad for state here. So I say, well, I'm actually carrying around the state. So I'm actually handling a function. I have a function S. I have a current state S. So I pass to K the current state S, and I continue in state S. Whereas the way put works is it ignores whatever state we're in. It passes to K the unit, because the result of put is a unit. And then it continues in the new state S prime. If and when a value is computed, then you just throw away the store and return the value. And this finally is like the Haskell thing that's actually runs the monad, that initializes the monad. So I'm initializing with the value 0. And so this is supposed to work as well if I didn't produce too many problems here. So let's try. And here is it works in this one instance at least. Okay, so
in your example,
yes.
In your example, the state is a natural number.
In this example, the state is a natural number. Yeah. And the reason why it's an integer is because I'm initializing it with 0 here. But these are polymorphic references, so I mean, the language computes the fact that it's got an integer. Okay, so let's now let's look at the epsilon. So I'm going to use intentional features. Okay, so what I'm going to use is I'll do it like this. I declare that there is an effect type. I define an effect type, which has just one operation called search. And so this operation expects an integer, and it returns a Boolean. I will not actually compute the witness. Remember, the epsilon is supposed to produce a witness. I will actually compute a neighborhood of the witness, and then I will convert, and then I will find, after that, I will find just one point in my neighborhood. So then I have to remember what are the neighborhoods. Remember, we are in counter space. So my epsilon goes from the counter space. So I'll write it like this. Well, actually, from 2 to the 2 to the n, like that. Oh, I have an eraser, but it's kind of small. I haven't figured out how to make it large. So I get my p, and I'm supposed to produce the sequence alpha here. I will do this in 2 steps. I will first compute a basic neighborhood of the sequence. And then after I know the basic neighborhood, I will just pick some alpha in that basic neighborhood. So a basic neighborhood here can be thought of as an initial segment, or it can actually be thought of as a prescription which prescribes finitely many values of alpha. So I'm computing an associative list which says at this point alpha has to have this value, at this point alpha has to have that value, and so on. So that's what I want to compute. Maybe we can look at the epsilon first, just so that you see what the thing up there does. Okay, so epsilon, upon getting p, is going to compute a neighborhood. It's this list here. It's an associative array. So then to convert this to a function, I say, well, it's a function which takes n, and now search whether the value at n is prescribed. If it is prescribed, then it has to be b, return b. Otherwise, just return true. Yes? So now we want to know what the find neighborhood does. Here's the complicated thing. Okay, so just like with the modulus, where it was important that I generated a fresh ref, which was secret, and only the modulus function had access to it, I now create a new instance of the searcher effect, which is this is now an effect which is defined just for the purpose of this epsilon. And what I do is this. I pass to my p the searcher. Just like in the modulus, I passed to my f the specially crafted b. I got an a, I crafted a b, which was special. It did something with references, and I passed it to p. And so as b was evaluated by, it did something. So the same thing is going to happen here. So I pass to p this operation, search. Now here's the handler, which explains what happens when p actually attempts to evaluate its argument at some value n, where k is the continuation that I have to answer. I have to answer either with true or false, because search has to produce true false. This operations s search has to produce true or false. So I have to pass to k either true or false. Just like before, I'm going to carry around state, except this time the state is not just one number, which was the modulus of continuity. It's actually the list that I'm building. So I'm in a state where I have so far built the list LST. First, I see whether maybe the answer at n is already prescribed by some previous parts of the search. If it is, then I pass to the continuation k the value v, the one that is prescribed, and I continue in the same state, LST. If no such answer has been prescribed, then what do? Well, I'll try both. I'll try answering true, and if that works, I'll accept that as an answer. Otherwise, I'll try false. So I pass to my continuation k the answer true here. I record the fact that at n, I answered as true. Yes, I add that to my state here. And when out comes, so the way things are structured here, what I will get out is the answer, so the value of p, and the state that was reached when the value was reached. So if out I get the answer true, then that's the answer. I found the answer true, and I know how I got there using this list, whatever came out. So maybe it's less confusing if I rename it like this. And so otherwise, if P answered with false, then, well, it answered with false, and the path, the neighborhood that gave me the false is irrelevant now because it's no good. Then I restart my continuation, K, and this time I pass false as an answer because true didn't work. If anything works, false is going to work. And I record the fact that at n, I answered as false. So that's how I handle the operation. How do I handle a value? That is, if P finishes, what happens when P actually finishes and it produces some Boolean value B? Well, in that case, I take the value it produced, I take the recorded neighborhood, and I return that as a result. And here's the final wrapper. So how do we actually start this? We start by initializing the list to the empty list. So in the beginning, I haven't tried anything, so nothing is prescribed. And then I take just the second component of whatever comes out, because what comes out is a pair, is the answer and the neighborhood. And I'm only interested in the neighborhood. Okay? That's the functional. And I'm just going to convince you that it works on one example. I can ask, give me, let's try the find neighborhood. It's better. Find neighborhood. And I say, give me, is there, so I'm going to evaluate A at 10, and I will want it to be different from A11. So I'm saying, find an open neighborhood of the Cantor space where the 10th term is different from the 11th term. And it says, here it is. If you set the 11th term to false and the 10th term to true, then that's going to work. If I turn this around, it gives me a different answer. It gives me a different neighborhood. So using the intentional features destroys extensionality of my functional. The one in Haskell was extensional, but this one isn't. There are various questions here that you could ask. For example, is it safe to mix the epsilons? So now I can have an epsilon inside an epsilon, or I can have an exists and then inside a for all and then inside an exists and so on. So these are questions about correctness of the implementation. This is maybe the main point I would like to stress is that while this is a cool program and it looks very complicated, but it's not really that complicated, and it's very nice and it's faster. In many examples, it's faster than the Haskell version. I don't think it's that easy to first formulate what it means that it works correctly, if it works correctly. I don't know, I haven't proved it. I don't know how hard it's going to be to prove that it works correctly. So Bas, you wanted to have examples of things to prove. Here are examples of things to prove. Prove that this actually computes the for all quantifier.
So what is the difficulty in the formulation of correctness?
So if you, first of all, so the easiest version would be when P, the predicate, is in some sense pure, right? You might want to prove that this works okay if P is pure. But then you get the question of what does it mean that P is pure? And maybe you can somehow get around it. You make a syntactic assumption about P or something. But then if you succeed in doing that, you will be tempted to show that this still works even if P, what if P uses something else and it seems harmless? Maybe P is using some memorization. That would be an example. And does it work if P memorizes things? I don't know. So I think there are a lot of questions here to be asked and answered. Yes?
Do you have a form of semantics for the language?
We have a semantics for the language which translates this into a domain. We have a domain theoretic version, but unfortunately not one in which effects can be locally generated.
Do you have an operational semantics?
We have an interpreter.
Yeah, but the interpreter is in a language with a formal semantic?
It's in OCaml. The interpreter is written in OCaml, and there is a version without the new name generation written in Coq.
Yeah. Would you be able to write it?
Yes. Bob, I suppose we are in the sessions. Yeah, okay, yeah. It's the questions, yes.
If I understand the code right, you're really using this search operation purely to sort of simulate a call CC.
I am using, yes, you could implement, so you could implement this same thing using delimited continuations and local references.
You're grabbing a control point at the moment where P evaluates that sequence.
Right.
And the reason you're calling K of whatever it is there.
Yeah, twice. I'm calling it once with false and once with true. Yeah.
To let it run to figure it out, and then that's where the prompt would come in.
Yeah, yeah. You could definitely rewrite this with prompt and with shift and what is it? The prompt and the shift. Shift and the reset.
So I agree that all of those things fall under the category of effects and all that, right? So I'm not disputing that, but it seems a little bit of a ruse, like to use F for this particular purpose. Like you could just as well have done this.
I wanted to show F because I couldn't. A long time ago, I wrote this in OCaml using the limcc library, and after I wrote the code, I couldn't understand it anymore. And it's easier to understand it in language I actually designed. So. Sorry?
Can you get it with just in exceptions? Do you need the CC?
Here, so for the, well, actually, you're asking, is it enough? So you don't need any effects to implement Epsilon.
But in this way?
In this way, you need continuations because I am using continuations. See, I'm restarting the same continuation twice. But there will be many other ways of using effects to implement Epsilon. So you could use exceptions, of course, yes. Yes, you could use exceptions, but then it's going to work differently. It's not going to work like this. Yes.
And so you do these computations which are, impure and not extensional. But in the end, often you just define an extensional function. Right?
Yes, so that's an important point. I wrap my effects with handlers so they don't propagate outside. However, there is a ghost of effects because my functional is not extensional anymore. After all, I'm finding neighborhoods here.
Yeah, I understand,
yes.
But then I use the neighborhood to compute something else, and that's my experience. So maybe I'm only interested in the external functions which I can define.
Yeah. So it's going to be like this. Neighborhood and epsilon are not extensional,
sure.
But then exists and for all are again extensional.
Yeah.
Yes.
So I wonder, have you any idea, is there any set of combinators which give you all extensional functions which you can define using one of these combinators? Or?
Don't ask me. Ask someone else. I don't know.
Okay, let's have one more question.
Yes.
So a while ago, John Longley proved that in ML you can define new extensional functions using effects. How does that compare to that?
Yes,
Have you come across a new extensional function which is not definable in a pure language? So he had a function he called capital H.
Yes, it was the A. Yes, he could do the H here.
The sequentially realizable functionals.
Yes, that's an interesting question. You should be able to compare. Yes, thanks for it.
Bob will be mad at me if I
So this also reminds me of the code for the excluded middle. Right, so you have in your head how that code works. The proof, so to say, using effects, you can provide a proof of the law of the excluded middle in a constructive way, right? Do you have that code in your head?
Not exactly.
Okay, then it won't be hard for me to ask my question.
Okay.
So it's the same idea. That's basically the point. You backtrack, right? You go and you commit to an answer, and then you see if you get caught out. And if you get caught out, you say, "Oh, I changed."
Right.
my mind." Okay. So is it? I don't remember. Is it true that you can define? I think it maybe is excluded middle follows from having Hilbert's epsilon or something like that. No. It's a choice operator. No. Am I misremembering?
Well, usually the excluded middle is related to Peirce's law, which then goes more directly to continuations. So, but I don't know. Actually, it's
The immediately decidability of pi 0 1 propositions, and in Hilbert's epsilon operator, when you don't get full tension on that, a fair amount of it.
Okay.
Okay, well, this is a good conversation to continue. Let's take a 5-minute break to allow the next speaker time to set up. Let's thank our speakers.